Okay, today I have the pleasure to have two different seminars. First, a seminar by Professor Yudu from Sun Yat-sen University. Yudu is a leading researcher in mesoscale dynamics and severe weather, focusing on low-level jet, gravity waves, cold pools, and diurnal cycle of coastal rainfall. He received his PhD in meteorology from Beijing University after earning a BS in physics from Beijing Normal University. He has been visiting professor at Ankara and University of Hawaii at Manoa. And also he had a research scientist role at IBM Research. He joined Sun Yat-sen University in 2017 and was promoted to full professor in 2022. Now I shortly introduce also Yang Bang, who is an associate researcher and deputy director of the Center for Natural Disaster Research at the Institute of Geographic Sciences and Natural Resources Research of the Chinese Academy of Science. Her research focuses on mountain precipitation and associated disaster effects. She has extensive experience in field expedition, research, and science communication on climate simulation and hazard effects in high-altitude mountain region.
E non ho capito perché si è persa.
Sante, ti sentiamo. Including the Qinghai Plateau, the Himalayas, the Aingduan Mountains, and the Tian. And also we have Jiazi Ke. Yes. A brilliant, I would say, postdoc at the Institute of Geographic Sciences and Natural Resources Research of the Chinese Academy of Science. And he has been, he did his PhD at Geneva, now he's working as postdoc, and he will soon move to Austria at Bochum University. So I suggest to proceed in this way. First, we have a seminar, then we have the presentation, and then we have a discussion section. So, please.
Okay, thank you, Michelle. So, good morning, everyone. I'm Edu from Yat-sen University. I'm so glad here to have a seminar to talk about heavy rainfall in South China. Today, I will focus on the three mesoscale factors, including low-level jet, gravity waves, and cold pools. Doesn't work. Let's see.
No?
No.
Sit here.
It works. Yeah.
Okay.
Okay, maybe I still. Okay, so let's start with some background. There are 5 rainfall hotspots in South China during the pre-summer rainy season. 3 of them are inland and 2 of them along the coast. Actually, there are 2 types of heavy rainfall in this region: front heavy rainfall and warm sector heavy rainfall. Front heavy rainfall is a classical type that occurs near the front, like this. But sometimes you can see heavy rainfall can occur far away from the front and in the warm sector region. And it often occurs near the coast region, and it is very difficult to forecast due to the absence of the synoptic forcing. So there are several mesoscale factors influence this kind of warm sector heavy rainfall, including low-level jet, gravity waves, and the cold pools. So today I will focus on these 3 important mesoscale factors one by one. The first one is low-level jet, which is one of the very important environmental factors influence for the heavy rainfall formation in this region. Actually, low-level jet can be classified into 2 types. One is the boundary layer jet. We call it BLJ. It occurs in the boundary layer and associated with the boundary processes. But another one is synoptic weather system related to low-level jet. It occurs higher than BLJ within 1 to 4 kilometers height, and it's always associated with the synoptic forcing. And so in South China, kind of this is a BLJ and this is SLJ, it's higher. And in South China, both type of low-level jet can occur at the same time and at the same place. and coupled together, we called it double jet. So we found that in this region, double jet can together produce the mesoscale lifting to trigger one sector have rainfall near the coast. So you can see that both type of low-level jet occur at the different levels. The BLJ at 915 millibor occur over the South China Sea, and at the axis of the BLJ, it occurs convergence near the coast. And at the 700 millibor, there is SLJ over here. This is south of the shear line or front. So the entrance of the SLJ, it will have divergence near the same place. So they will boundary convergence and the middle level divergence together produce mesoscale lifting near the coast to trigger one sector have rainfall. So we called it coupling of the double level jet. And this phenomena is, we also have observed not only the South China, other places, we also see the similar phenomena. So such as the Henan have rainfall in the middle of China, and in the middle reaches of the Yangtze River in the May season, and even over the Grand Plains of the US, we can also see some kind of the double low jet coupling. And compared to the SLJ of the land, the BLJ over the ocean is very critical because lack of observation of the ocean, we don't understand the behaviors of the marine boundary jet so yet. So we propose two scientific questions. What are the basic characteristics of the marine boundary jet, and how about their forecast? The other one is how does this marine boundary jet influence coastal rainfall in South China? To answer the first question, we conduct a field campaign over the North-South China Sea with scientific research ship, which provide a good opportunity to examine the marine boundary jet in this region. We release the radio sound 4 or 6 times a day, and this video shows me the releasing. Let me see. Yeah, this video shows me releasing the weather balloon on the ship dock. So this map shows the ship route, and you can see the vertical, the evolution of the vertical wind profile indicate multiple low-level jets. Some of them BLJ indicated by the blue, by the green. Let me see. No mouse. No. I cannot point. Right? Oh, it's here.
You can see the. Yeah.
Can I check this? Where is it?
What you need?
It's a
Pointer.
pointer. Yeah. Yeah, this one. Great. Okay. Great. So you can see here is some boundary layer jet within 1 kilometer indicated by the blue dots. Some of them are SLJ within 1 to 4 kilometers indicate SLJ. And interesting, you can see the BLJ and the SLJ become more active after monsoon onset. And the low jet exhibits the very strong dynamical cycle with maximum and night. And we also compare the performance of the full global wind analysis data set compared to the observations. So you can see the wind analysis data set overall produce the evolution of the low-level winds. But if you focus on the dots or triangles, you can see they significantly underestimate the currents of the marine boundary jet. But among them, ERA5 is the best according to the RMSE and the BICE. So we use the hourly ERA5 dataset to see the climatological features of the marine boundary jet. And you can see the 2 jet hotpots on either side of the highlight islands, which refers to the BLJ West over here and the BLJ East over here. And they both occurs at 915 millibor, it's pretty low. and they show significant dynamic cycle with maximum at night, and they show significant seasonal variation during the pre-summer rainy season. And they have the dependence on each other, so they always strengthen together. So to obtain the more accurate marine boundary jet product, because the ERI5 is not very good, so we try to produce the more accurate jet product. So we use the UNet-based deep learning method to try to retrieve the marine boundary jet. So we train this model using the ERA5, and they can map the sea surface winds to the boundary layer winds, and then we use the real satellite sea surface winds to predict the winds at 915 millibor, which is the level the marine boundary jet typically occur. And we validate the result using the radio sound and light observation on ship. So according to the RMC, MAE, and R, you can see the UNet model is better than ERA5 for capturing the marine boundary jet. And we also compare the forecast performance of the AI model and the numerical model. AI model, I use the Pangu model. Numerical model, I use the ECMWF. So you can see, interesting, they show kind of the opposite arrow structure. The Pangu model tends to underestimate the jet with the high miss-along rate, and the ECMWF tends to overestimate the jet with a high false-alarm jet. So based on this complementary arrow structure, we try to combine them to produce the better forecast product using the UNet model. So we combine the Pangu model and the ECMW model to take them their advance. So you can see this blended model performance significantly significantly performance compared to the individual model relative to their RMSE and the area, the extent of the jet, intensity of jet, and direction of the jet. And here I show you how the marine boundary jet influenced coastal rainfall in South China, and you can see the evolution of this jet can significantly moderate the coastal rainfall. So, before the CI, the convection initiation, you can see the jet is relatively weak and southwesterly, and the convergence or lifting occurs at the edges or terminus of the jet, and not influence the coastal area. But after midnight, the jet gets enhanced and turns to southerly. So you can see the lifting on the edges of the jet become stronger and also affect the coastal area. And we also check out the role of the coastal terrain, and we identify the three lifting mechanisms. One is, I just mentioned, the convergence by the jet, the terminus of jet. And another one is terrain lifting kind of, and another one is the frictional convergence between the land and the sea. So we quantify these three lifting mechanisms, and they make roughly equal contribution to lifting. And here I show the relationship between the marine boundary jet intensity and the coastal heavy rainfall intensity. It is interesting, they are not simple linear relationship. We find the moderate jet can produce heaviest rainfall rather than stronger jet, because the moderate jet can produce stronger lifting and also avoiding the larger thing. So the kind of the combination, the dynamic effect and the coastal effect and the thermodynamic effect. And we also use the observing system simulated experiment OC to examine the sensitivity of the coastal heavy rainfall to marine boundary jet. And we perform the 21 ensemble members, you can see some member can capture the coastal rainfall very well, but some member cannot capture the rainfall at all. So we compare the good member and the bad member. This figure shows the difference in 950 millibar wind field in the initial condition. So you can see some difference. This is the northern point. This is northern point located at the terminus of the jet, and this is the southwestern point located to the upstream of the jet, and this is the southeastern point located kind of the eastern front of the jet. So we try to simulate those wind profiles at these 3 points from the good member to try to improve the bad member to see what happens. So interesting, you can see that in the bad member, there's no rainfall at all. But after simulating those wind profiles at that 3 points, you can see the rainfall has improved. And you can see if we simulated the 3 points, that will be best. That's the best. But if we just simulate the point at southeastern point, that's not good. Why? Because you can see in the bad member that this kind of the jet is weak. It's weaker compared to the bad member, compared to the good member. But after simulating those points, you can see that the jet becomes more pronounced and the structure is better represented. And so wind profile simulation can improve the representation of the marine boundary jet and the strength, and this improve the coastal heavy rainfall forecast. Okay, this is the first part. Let's move on to the second part, as GravityWaves. And GravityWaves is a very common phenomenon observed in the atmosphere. There are several sources generating GravityWaves, including mountains, frontal jet, dynamic cycle, and convection. But today I focus on the source of the convection because it is very complex, because convection can generate GravityWaves, and the GravityWaves may in turn trigger convection. And so how does the convection generate GravityWaves? A popular mechanism is step-back heating released by convection. If the convection heating is deep with maximum at the middle level of the troposphere, they can produce a deep wave downdraft propagating outward from the convection. And according to the nodes of the heating profile, we call it N1 wave. But if convection evolves into the stratiform with high-level heating and low-level cooling, they can produce the N2 waves with high-level descent and the low-level ascent. So the N1 wave downdraft propagating outward tends to stabilize the environment. So you can see after N1 wave pass by, so you can see the Cape significant decreases. But the N2 wave with low level lifting tends to destabilize the environment. So you can see after passage of the N2 wave, you can see a decrease in LFC. That's a variable for the elevated convection. So in words, the N1 wave suppress convection and the N2 wave favor convection nearby. Okay, and we conduct idealized simulation of a spore line with strong vertical wind shear. During the development of the spore line, convective GravityWaves are evident propagating outward from the spore line. You can see the N1 wave and N2 waves, and we further use the spectral filtering to objectively identify the N1 wave and N2 wave. The solid line here indicates N1 wave, and the dashed line here indicates the N2 wave. So the harmonic diagram of the cloud wafer show that the 4 cloud decks, 1, 2, 3, 4, sequentially generate the in front of the spore line, which is associated with the cyclonic generation of the GravityWaves. Specifically, the N2 wave induce the formation of the cloud decks, and N1 waves suppress the cloud desk. Okay. And one interesting phenomena is convection initiation ahead of the score line. In our idealized simulation, we identified the 582 CI events within the 8 hours. CI events show significant periodic oscillation, and primary as the distant event, that is greater than 5 kilometers from the gas front. Okay, but for the CI near the gas front, they show the stable frequency that is indicated by the blue lines here, and this kind of the distant CI event are mainly driven by the cyclonic generation of the N2 waves, and the significant associated with stronger cold pool and the higher rate of reflectivity. These N2 waves characterized by the high level descent and the low level ascent can promote CI by moistening the environment, enhancing its stability. That's a variable for the CI. Okay. Next, I will show you a real case. Before that, it's the idealized simulation. Now I show you a real case in South China to illustrate the impact of the convective gravity waves on convection. Near the coast of South China, one sector has rainfall often occur away from the frontal rain band on the northern side, and the one sector has rainfall is difficult to forecast, I just mentioned, due to the absence of the frontal lifting. The first part I show you, low-level jet plays an important role for the one sector rainfall, but the one question arises, can frontal rainfall influence one sector rainfall? The answer is yes, through the gravity waves. So you can see two N2 waves propagate southeastward from the frontal rain bands. And this harmonic diagram clearly shows the two passages of the N2 waves with propagation speed of around 20 meters per second and the propagation distance of larger than 300 kilometers. And you can see the potential temperature lags vertical motion that satisfies the polarization relationship of the gravity waves. After passage of the N2 wave, you can see the low-level relative humidity increases and the sin decreases. That's a variable for the development of the one sector convection. So this thematical diagram summarizes this story. The front hair rainfall on the north produced the N2 wave through the late heating and the cooling. And these waves propagate ahead of the frontal rain band and change the convective environment along the pathway that is conducive to the initiation and development of the one sector convection. Okay, finally, I'll talk a little bit cold pools. So a cold pool is formed by the descent of the cold air due to the precipitation, evaporation, and the cooling. And the cold pool will propagate as the density current and plays an important role in convection initiation and growth. And many studies have examined the cold pools by observation and the high resolution simulation. And the cold pools in different regions show different characteristics. But now, observational characteristics of the cold pool in South China coastal region remain unclear. So to address this problem, we used observation from the Shenzhen Met Tower, which is the very high, which is the 356 meters, which is the first highest first highest in the Asia and the second highest in the world. So we use this tower provide measurement at 13 vertical levels, and this unique data set allows us to directly observe the vertical evolution of the cold pools. And using the data from the 2018 to 2020, we totally identified the 167 cold pool events. Our analysis showed that the cold pool occur most frequently during the rainy season from June to September, and they show dynamic cycle with maximum in the afternoon, which is consistent with the dynamic cycle of the convection and the precipitation. And after the passage of the cold pool, we typically observed a decrease in temperature, increase in pressure, and a rise in relative humidity, which these changes being more pronounced at lower levels. At the same time, the specific humidity decreases and the wind speed increases more at high levels. On average, the thickness of this cold pool is about 670 meters, which is thicker than the typical cold pool over the tropical oceans, like 300 meters. Under the influence of the marine boundary jet, you can see the cold pool tends to be weaker. Why? Although the marine boundary jet can produce can transport moisture to that region that can produce the stronger convection, but why the cold pool is weaker? So we find that because the jet environment has a higher humidity that suppress the precipitation evaporation and the weakening the intensity of the cold pool. It's one reason. The other reason is boundary jet has a very strong vertical wind shear and turbulence. They can increase the heat exchange between the cold pool and the environment, and further weakening the cold pool. Okay, pre-study find that the environmental low-level wind shear interacting with the cold pool plays an important role in convection initiation and growth. The optimal state is near balance between the positive horizontal vorticity by wind shear and the negative horizontal vorticity by cold pool, which is the famous RKW theory. But pre-study only consider this simple linear with vertical wind shear. But how about the more complicated situation like low-level jet? We know low-level jet is not a simple linear with wind shear. So we try to better understand the interaction between the cold pool and the low-level jet. We conducted the idealized simulation using CM1, and the wind profile here set as a low-level jet with maximum speed of the 15 meters per second at 600 meters, which is similar to the marine boundary jet I just showed before over the South China Sea. And in comparison, two additional scientific experiments are also performed. The blue line is no wind, and red line means the linear shear as RKW theory. So firstly, I'll show you the evolution of the cold pools on the influence of the low-level jet. So blue contours here represent the negative temperature perturbation, indicating the cold pool. So the shading means the vertical motion. So you can see the low-level leading edge of the cold pool can gradually propagate rightward due to the weak background wind near the surface. But the main body of the cold pool is blocked at the original location due to the very strong wind at the level of the jet core. So the cold pool seems like it evolves into the two-step structure, and with the two separate significant vertical motion regions here and here at the two kind of the cold pool heads. And we further compare the cold pool evolution with the two other scenarios, no background wind and the linear wind shear. So you can see the cold pool in these two scenarios only don't show the two-step structure. They only have one significant vertical motion region here and here. But in the low-level jets case, you can see the two regions here and here. Okay, that's different. Okay, and we can see the vertical motion is the strongest in the shear scenarios, in the linear shear scenarios, because the strongest interaction of the cold pool and the strongest wind at the surface in this case. And if we include the moisture in the model, convection can be triggered earliest in the linear shear case, the red line here, and which is consistent with the strongest vertical motion in the dry simulation before. However, the convection intensity indicated by the fraction of the reflectivity larger than 45 dBz or 50 dBz, and you can see the low jet case becomes strongest. The convection becomes strongest rather than linear shear case. So how does it happen? According to the partial trajectories of the convection is elevated in the low level jet case, but convection is a surface-based in the linear shear case. Based on the vertical distribution of the cape, elevated cape is slightly larger than surface-based cape. So that's why low level jet case can produce stronger convection. And if we look closer at the partial trajectories in the low level jet case, interesting, there are two main clusters of the trajectories, class A and class B. We found that class A trajectories mainly come from the level above the jet core, okay? And class B mainly come from the level below the jet core. So why? So if above the jet core, so the horizontal verticity is positive, and the horizontal verticity induced by the cold pool is negative. They can balance and produce the upstream motion. But for the class B, below the jet, then the horizontal verticity is negative, and the cold pool driven by the horizontal verticity driven by the cold pool is also negative. They will produce the more inclined to backward to the cold pool side. And in the mature stage, due to the negative horizontal verticity associated with the cold pool and the shear line below the jet core induce the strong tilted partial trajectories, contributing to the expansion of the stratiform region. Consequently, the low-level jet produce the greater fraction of the high radar reflectivity, but for the near shear case, produce the heaviest heavy rainfall and the stronger surface wind in the convective regions. So this thematical diagram summarizes how a low-level jet interact with the cold pool to drive convection during the initial stage and the mature stage, compared with the classical linear vertical wind shear scenarios. Okay. Finally, I will summarize the key point in this talk. We using these conceptual diagrams, low-level jet, graduates, and the cold pools jointly influence coastal heavy rainfall in South China. Double low-level jet together produce mesoscale lifting near the coast. for the heavy rainfall, and the marine boundary jet is more critical due to the lack of the observation of the ocean. So we try to reconstruct the marine boundary jet and using the AI method, and we also try to produce the better focused the product combining the AI model and the numerical model. And in South China, we found that the front rain band can produce the graduates through the late heating and cooling, and these graduates can propagate ahead of the front rain band and change the convective environment along the pathway, which is conducive to the development of the warm sector convection, and the interaction between the low-level jet and the cold pool is different from the classical RKW theory. The cold pool will evolve into the two-step structure, and under influence of the low-level jet, and their interaction produce elevated convection rather than a surface-based convection, and its thread form becomes larger in the low-level jet case compared to the linear shear case. That's all I have. Here I list some reference I just mentioned in this talk. If you are interested, please check them out. Thank you for your attention.
Thank you. I have a long list of questions, but
Yeah.
I will also. For me, it was extremely interesting because I can find a lot of analogies with Italy. Probably some points in Italy are not well investigated.
Yeah.
So I will have several questions, but I think it's better.
Okay.
To answer the other
Sure.
question.
Sure.
Okay.
Let's see if it starts. Okay.
Okay. Good morning, everyone. My name is Yan Huang. It's my pleasure to be here to give a brief of our institute and share our recent work of my group. I see here. Okay. Our institute is the Institute of Geographic Science and Natural Resource Research, Chinese Academy of Science, and in our institute there are six library. The first one, including the land surface, regional development, resource use and GIS, and ecosystem and water cycle, and our center is belong to the first one, land surface part and simulation lab. And our center name is Natural Disaster Resource Research. Our work is focused on the disaster geography, disaster maintenance, disaster risk, and disaster reduction. And my group is in the first part. And our group is more focused on the mountain climate and mountain weather, and its disaster impact, especially that we focused on the mountain precipitation, including rainfall and snowfall features, and its impacts on the mountain disaster, including snow avalanche, floods, and snow drought. And today I will share our recent works. The first one is about the risk of extreme rainfall. we focused on the warming and heavy precipitation driven surge in floods over the high mountain ISAC, especially over the west of the Tibetan Plateau. Because in our province work, we found that over the Karakoram, the globes have appearance of the cycles of the kings. So the first question is that how does the climate drive the cycles of the globes? And today, because I just wanted to give a brief of our work, so I didn't show more details of this result. And the second work is about the extreme rainfall, about the major floods. Most of them are driven by the extreme rainfall, especially, for example, during 2022, the Pakistan experienced a spring heat wave and summer major floods. So in this study, we use the wolf model we also use the wolf model to explore the orographic precipitation contribution to these major floods. So and this work I have published. And the other the other work is about the risk of abnormal snowfall. So for the abnormal snowfall, we analyze it from different way. So for the excessive snowfall, we know it may be lead to the snow avalanche and the snow melt flood and snow white disaster, for example. But we more focused on the snow avalanche. And for the insufficient snowfall, it will lead some snowdrift. And the snowdrift also further lead to result in the wildfire and dust storms. So for focused on the in our province work focused on the different features of the snowfall. We did some work. We know as the climate changing, including the northwest China, there are many snow cover, but as the climate warming, so the snowpacks declining, and but the snow disaster is not decreased because at the same time, the extreme snowfall is increasing, especially the heaven snowfall is more and more. So we focused on the northwest China, we collect multi data and use multi-method to analyze the climate change and the extreme weather impacts on the snow avalanche and the snow method. Especially for the snow avalanche, we also collect some tree ring observations and from the different singles on the tree ring. So we reconstructed the avalanche history and to further analyze the climate change on the snow avalanche over the northwest China. So we found that as a climate warming reshaping the snow avalanche activities, especially from the tree. It shows that the avalanche activities is increasing as the climate warming, because the climate warming will change the snowpack properties. Especially it increasing the snow density, and ice the increasing frequency of the heavy snowfall events. So the snow avalanche, especially the white snow avalanche, is increasing, and its onset time is earlier and earlier. And we found that actually in this result, we found that as there will be 8 days. There will be 8 days earlier onset when the temperature increased 1 degree. So the result, the second result is about the snowdrift. So we also found that as climate change, the risk of the snowdrift, especially the warm dry snowdrift, is increasing in northwest China. And in this work, we classify the total snowdrift into 3 different tables, including the warm-only snowdrift, which is driven by the warming, and it leads the weak accumulation and strong ablation. And the other table is dry-only snowdrift. It is because of the persistent precipitation deficit. And the third one is a warm dry snowdrift. It because of the together impacts of the long-term snowpack deficit and there's under the hydrothermal stress. So, and we found that as our result, we found that before the 2000, in northwest China, the dry only snowdrift is dominated, but after 2000, the contribution of the warm dry snowdrift is increased. Okay. Okay, to conclude, I give some take-home messages as follows. And in the precipitation, there's some publication in our group can support this work. Okay, thank you.